has more turns than the primary, the secondary voltage is higher than the primary, less than the primary. Oh. Hmm? Secondary has more turns than the primary. That means it's higher than the primary. Which of the following is not a typical frequency rating for a power transformer?
120.
With zero losses assumed for the transformer, the power in the secondary right, assuming zero losses, it's always equal to the primary power in the primary. That being said, and everything that I just preached to you about remembering for those turns ratio problems that primary power equals the secondary power, there is something called loss. And that's where true power versus apparent power comes into play with transformers. It's confusing. It can be confusing. It's not super critically important for this class than to understand. What I want you guys to understand is that there's, in an ideal world, everything would happen mathematically perfect, right? If you were able to measure the primary power and able to measure the secondary power, they should equal each other. But there is a little bit of loss because that transformer is doing some work, right? That loss comes in the form of heat. So they use VA, kVA to measure true power versus apparent power. And there's a video that I will show you guys that explains it in a language that I'm sure everybody in here can understand. They use beer. Oh, crap.
You have no idea which.
Get out of here. Maybe some of them. Mhm. Hmm. Maybe I'll put it in a different playlist. There it is. You see the beer?
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing power factor. We're going to start off really easy with some simple analogies to help you understand the basics, and then we'll advance it into electrical engineering terms with some worked examples, as well as looking at what is power factor, what is a good and bad power factor, what causes bad power factor, and how to fix bad power factor. So what is power factor? Power factor is a unitless number using alternating current circuits. It can be used to refer to a single piece of equipment, such as an induction motor, or the electricity consumption of an entire building. In either case, it represents the ratio between true power and apparent power, the formula being PF equals kW divided by kVA. So what does that mean? My favorite analogy to explain this is to use the beer analogy. We pay for beer by the glass, but inside the glass there is both beer and foam. The more beer we have, the less foam there will be, so we get very good value for money. If there is a lot of foam, then there's not a lot of beer, and so we're not getting very good value for money. The beer represents our true power, or a kW, our kilowatts. This is the useful stuff we want and need. This is what does the work. The foam represents our reactive power, or a kVAR, kilovolt amps reactors. This is the useless stuff. There will always be some, we have to pay for it, we can't use it, so we don't really want much of it. It does actually have a use and a purpose, but we'll see why later in the video. The combination of these kWs, our kilowatts, and a kVAR, the kilovolt amp reactive, is our apparent power, or our kVA, meaning the kilovolt amp. Power factor is therefore the ratio of useful power, or true power, in kilowatts, or kW, divided by what we're charged for in kVA, kilovolt amps. So it's telling us how much value for money we're getting for the power we consume. If we briefly touch on electrical engineering, and I will keep this part brief, then we might see this expressed as a power triangle. In this case, I'll draw it as a leading power factor as it's easier to visualize. The beer, or true power, is the adjacent line. Then we have the foam, which is the reactive power on the opposite. Then for the hypotenuse side, which is the longest side, we have the apparent power. This is at an angle from the true power. The angle is known as theta. You see, as the reactive power, or the foam, increases, then so does the apparent power, or the kVA. You could then use trigonometry to calculate this triangle. I won't in this video, as I'm just covering the basics, so we'll just see the formulas you need, but we'll do some calculations and worked examples later in this video. If we look at a typical residential electricity bill, then we'll typically see just a fee for the amount of kilowatt hours used, because the power factor and the electricity consumption will be very low. So electricity companies tend to not worry about this. However, in commercial and industrial electricity invoices, especially buildings with smart or interval electricity meters, then we'll likely see charges and information for the amount of kilowatts, kilowatt hours, kilovolt amps, and kilovolt amps reactive used. Large buildings in particular will often see reactive power charges in there, but this depends on the electricity supplier and the agreement they have with the consumer. The reason they charge a penalty for this is because when large consumers have bad power factors, they are increasing the current flow through the electricity network and causing voltage drops, which reduces the supplier's distribution capacity and has a knock-on effect to the other customers. Cables are rated to handle a certain amount of current flowing through them. So if a lot of large consumers connect with bad power factor, then the cables could overload. They could also struggle to meet the demand and the capacity agreements, and then no new customers will be able to connect until they either replace the cables or install additional cables. Reactive power charges occur when the power factor of a building falls below a certain level. This
It can transform a photo into a wallet.
level is defined by the electricity supplier, but it typically starts around 0.95 and below. A perfect power factor would be 1. However, in reality, this is almost impossible to achieve. We'll come back to this part later in the video. In large commercial buildings, the overall power factor is likely to sit in the following categories. Good power factor is generally between 1 and 0.95. Poor power factor is anything from 0.95 and 0.85. Bad power factor is anything below 0.85. Commercial office buildings are usually somewhere between 0.98 and 0.92. Industrial buildings could be as low as 0.7. We'll look at what causes this shortly. Let's first have a look at an example. If we compare two induction motors that both have an output of 10 kilowatts and are connected to a three-phase 415 50 Hz supply, one has a power factor of 0.87 and the other with a power factor of 0.92. Both motors will deliver 10 kilowatts of work, but the first motor has a lower power factor compared to the second one, meaning we're not getting as much value for money. The first motor will need to draw 11.5 kVA from the electricity grid to provide the 10 kilowatts of power. The second motor will need to draw just 10.9 kVA from the electricity grid to provide the same 10 kilowatts of power. This means the first motor has 5.7 kVARs and the second motor has just 4.3 kVARs. Remember, our kilowatts is the beer and that's the useful stuff. The kVARs are the foam, that's the not so useful stuff. The kVA is what we're going to pay for, and that's the kilowatts and the kVAR combined. How did I calculate that? For kVA, I used kilowatts divided by power factor. So 10 divided by 0.87 to get 11.5 kVA. For kVAR, I use the square root of kVA squared subtract kilowatt squared. So the square root of 11.5 kVA squared minus 10 kilowatt squared. We could have also found the power factor from the kilowatt and the kVA using 10 kilowatts divided by 11.5 kVA. We could have found the kilowatts from the power factor and the kVA using 0.87 divided by 11.5 kVA to get 10. So what causes poor power factor? In most cases, the power factor is affected by inductive loads. If we have a purely resistive load, such as an electrical resistive heater, then the voltage and the current waveforms would be in sync or very close. They would both pass through their maximum and minimum point and then pass through the zero axis at the same time. The power factor in this case is 1, which is perfect. If we drew a phasor diagram, then the voltage and current would be parallel. So all the energy drawn from the electricity supply goes into doing work, in this case creating heat. But if we took an inductive load, such as an induction motor, then the coil's magnetic field holds back the current and results in a phase shift where the voltage and the current waveforms fall out of sync with each other, so the current passes through the 0 point after the voltage. This is referred to as a lagging power factor. Earlier in the video, I said the foam or the kVAR is useless. That's not exactly true. We actually need some reactive power to create and maintain the magnetic field which rotates the motor. The reactive power is wasted in the sense that we get no work from it, but we still have to pay for it, although we do need it to be able to do the work in the first place. If we drew a phasor diagram for a purely inductive load, then the current would be at an angle below the...
Notice anything about those sine waves? This is a purely inductive load. See how the peaks are not lined up? Why? Starts with an I and rhymes with Schminductive reactance. Remember, capacitive reactance shifted the sine wave the other way. So current, the red one, was actually before the peak of the blue one. That's the effect that an inductor has on an AC circuit. Okay, so just keep that in mind, because everything we just learned about capacitive reactance, we're now going to move to inductive reactance. And what you'll learn by the end of that, the next 3 chapters, is that you can use them to offset each other, right? And line those peaks back up. Anyway, we just wanted to point that out to you. Oh, they even show the phasor diagrams.
the voltage line, meaning not all the electricity consumed is doing work. If we took a purely capacitive load, then the opposite happens to the inductive load. The voltage and current are out of phase, except this time the voltage is held back. This causes leading power factor. Again, this will mean that not all of the electricity being used is being used to do work, but we still have to pay for it regardless. If we drew a phasor diagram for a purely capacitive load, then the current line would be at an angle above the voltage line as it's leading. Correcting poor power factor. What can we do to correct poor power factor and reactive power charges? In most cases, we come across lagging power factor caused by inductive loads. To correct poor power factor, we can add capacitors or inductors to the circuit, which will realign the current back into phase and bring the power factor closer to 1. If we have a lagging power factor caused by high inductive loads in the circuit, then we add capacitors. If we have a leading power factor caused by high capacitive loads, then we add an inductive load to the circuit. These need to be calculated, and we'll see some example calculations of this at the end of the video. So why should we fix poor power factor? Poor power factor means you need to draw more power from the electricity network to do the same amount of work. Therefore, the cables need to be larger, so the installation is going to cost more money. If the power factor becomes too low, then the electricity supplier might charge you a penalty fee or a reactive power charge. Poor power factor can cause losses in equipment like transformers and leads to high heat gain. It can lead to voltage drop and can even reduce the life expectancy of equipment in extreme scenarios. Capacitor calculations for power factor correction. Let's look at a simplified example of calculating the size of a capacitor to improve the power factor of a load. The building has a 3-phase power supply and has a total load of 50 kilowatts of work. It also has a power factor of 0.78, but we want it to be 0.96 to avoid penalty charges. Currently, the building has a total apparent power, kVA value, of 64.1 kVA. And we find that by just dividing the kilowatts, 50 kilowatts, by the power factor of 0.78. It also has a reactive power of 40.1 kVAR. We find that by taking the square root of the kVA squared and subtracting it from the kilowatt squared. So take the square root of 64.1 squared minus 50 kilowatt squared. Then we calculate what the value should be if we had a power factor of 0.96. So our apparent power should be 52.1 kVA. We find that from 50 kilowatts divided by 0.96 power factor. Then we find our reactive power, which is the square root of the kVA squared minus the kilowatt squared. So the square root of 52.1 kVA squared minus 50 kilowatt squared, which gives us 14.6 kVAR. The capacitor therefore needs to make up the difference between these. So 40.1 kVAR minus 14.6 kVAR, which equals a 25.5 kVAR capacitor.
All right, a lot of that stuff is engineering stuff that we don't really care about right now. Is that helpful in understanding power factor? You guys have motors in your homes? Yeah, you do. Your dryers, your washing machines, your microwaves, your motors and all that. Are motors inductive loads? Yeah. So are you being charged for true power or apparent power? By Ameren. You're being charged for all of it. If you want to, you can call them and explain to them power factor, and the person on the phone will have no clue what you're talking about. But you can explain to them that they're charging you for more than you're actually getting out. You say, hey, lady, I'm paying for the foam and the beer, and I'm only getting the beer. Yeah. Well, there you go. You can use power factor however you want.
This is becoming a business class.
Right. All right, we're gonna get into some labs now. Is everybody logged in? I'm gonna take over your computer screen unless you got one. Get ready for me to hijack your stuff. A couple of you have turned in labs 16 already. I take it the rest of you are. I'm still gonna do 16. Right, so I'm gonna finish going through 16. I'm gonna hand out 17. In case those of you have. Okay, so you have 16 want to work ahead on this, you're more than welcome to. So I'm actually gonna go over. There's lab 17, but back to 16.
Copy of the 16. I'm not sure for my, I don't know if the phone that you will do that.
Copies of 16. No, but I can print one for you. You got it? Okay. All right, so going back to setting up the circuit. In table 19-1, remember, we're just going to use the capacity, the listed values. And then we got to set up our circuit. Right now, I've got my, what is this? 1K ohm resistor in series with my 0.1 microfarad capacitor. And I'm using the positive rail over here and the negative rail over here to make my connections to the function generator. But first I need to check resistance of my resistor with my meter. I'm getting 0.991 kilo ohms. Whoops. $991.09 ohms. Circuit is a series circuit, so the current in the resistor is identical to the current seen by the capacitor. You can find this current easily by applying Ohm's law to the resistor. Measure the voltage across the resistor VR using a digital multimeter. Record the measured value in table 19-2 in the column labeled capacitor C1. Compute the current in the circuit by dividing the measured voltage by the resistance of R1. Okay. So first things first, I need to set this circuit up. So sine wave generator. This is going to be my applied AC voltage. So circuit. And what do I want? 1 kilohertz. You can't read mine, but this is 1 kilohertz. And the amplitude of 1 volt RMS. Amplitude 1 volt, and then VRMS 1 kilohertz, 1 volt RMS, and I'm going to turn that output on. Now it's telling me that I can read the voltage drop VR across resistor 1 and put it in this column. So I will do that. AC voltage. What? What? Don't you bring my mother into this?
One of the one
What am I doing? Voltage drop across R1. Okay, so where's my meter read? Read my meter leads. I'm reading AC voltage. I'm just going to hook on to I'm getting a voltage drop of 0.49429 volts. So what is my total current? can find total current just by finding the current through the resistor, right? Zero point 4949. Oh, I set it on the window out there. Oh, all right. I think that'll work, but I'd wear safety glasses when I turn it on. I think it'll work. If it doesn't, it might just burn the lamp out.
Okay,
So,
all right. I'll
do you
get
want me
on.
to order you some more of those starters?
Sure, if you want, if you
Yeah,
feel like you
I
need to.
Yeah, they can't be that expensive, right?
Well, no, they're like on Amazon. I was gonna,
I'll order them.
all right, cool.
I mean,
I'd say just two, mechanic's coming in tomorrow to work on the presses. I don't even know if that one's bad. It was just laying around and I'm like, yeah, definitely, definitely.
everybody say hi to John.
Hey, say hi, John.
See you, John. Okay. 0.4949 divided by divided by 991.09. Remember, these are my numbers. Yours aren't going to be the same, but you understand where I'm getting at, right?
Yeah, I got 160.
So about 0.49 milliamps. Come on now. So this is the current through the resistor, which equals the total current, right? Because it's a series circuit. So I got 0.0499. I have to write it on lamps. 49. Nine, 3, 5. Voltage across the capacitor.
Yeah.
Measure the RMS voltage across the capacitor V sub C. This is procedure number 4. Record this voltage in 19-2, then use this voltage to compute the capacitive reactance using Ohm's law. So measure the voltage across the capacitor. I'm getting 0.8307 volts.
No.
Okay.
One volt. Okay. Right? Oh, okay, that's fair, okay. What? The circuit's not connected. Those five are connected, those five are connected. We don't want to all.
You guys know how your breadboards are set up? Have you been taught that?
Yeah.
Okay. So in procedure number 4, it says solve for capacitive reactance, which is the voltage that we just found divided by the current. X sub C equals B sub C divided by I sub C. I sub C is just equal to the total current. So we get 0.8302 divided by total current, 0.00049994. About 1,600 ohms is what I'm getting. Computed capacitance. Going back to procedure number 5, using capacitive reactance found in step 4, compute the capacitance using the equation C equals 1 over 2 pi FC. So I'm going to delete a bunch of this stuff so I can do some more math up here. Well, capacitive reactance formula. So if you switch these two, solve for capacitance, you have C equals 1 over 2 pi X sub C. So be 1 divided by 2 times pi times the frequency is 1,000, right? Times X sub C is 1,662.4 ohms. One divided by 2 times pi thousand times 662.4, right parentheses, equals. Zero point zero 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 This is going to be farads. Did I do that right? My calculator showing to the -8. So 1, 2, 3, 4, 5, 6, 7, 8. Yep. What does this equal about? Almost 0.01 microfarads, which is what it's supposed to be, right? Point 0.1 microfarad.
What is up with current and total current?
What did I get for total current? 0.4994 milliamps. All right, so this brings us on to procedure. This value should agree with the value marked in the capacitor and measured in step 1 with experimental tolerances. I'm supposed to get 0.1 microfarads and I got 0.096 microfarads. Pretty darn close. Number 6, repeat steps 3, 4, and 5 using capacitor C2. Enter the data in table 19-2 in the column labeled capacitor C2. I'm going to skip this step because I just went through how to do it with the first capacitor. You should be able to duplicate that. Now connect C1 in series with C2. The equivalent capacitive reactance and capacitance, this is procedure number 7, by the way, can be found for the series connection by measuring across both capacitors as if they were one capacitor. Enter the data in table 19-3 in the column labeled series capacitors. The following steps will guide you. All right, somebody stole my other 0.1. Microfarad capacitor.
Oh, I think that's you put it out there.
You're lying.
Okay. No.
Anybody else have an extra 0.1 microfarad capacitor? Anybody not using theirs? Use that too. Okay, so I'm gonna connect mine in series. I'll show you how I'm connecting mine. Wait. Wait, he did give it back. It's right there.
You have two?
So how can I do that? Yep. Is that a completed circuit?
You're putting the resistor in series with it?
Um, Check my
You
procedure.
calculate the capacity reactance, so you, make
Yes. Yes, we are. It doesn't say anything about taking the resistor out of the circuit.
Okay.
What did you ask, Lewis?
we calculate the capacity reactance. Somewhere.
How did I?
Yeah, we got the 1.6.
It's Ohm's law. If you follow the procedure on your lab, it says use Ohm's law to, right. All right, so anyway, that's how I have mine set up. You should be able to set your circuit up in series or parallel by now, but let me know if you're having any problems. Check that the generator is set to 1 volt RMS. Still is. Find the current in the circuit by measuring the voltage across the resistor as before and dividing the resistance. Enter the measured enter the measured voltage and the current you found in table 19-3. All right, so all of my stuff on the left over here, I'm getting to delete, just so everybody knows. I'm gonna put table 19-3 in there. So I'm still on 1 kilohertz, 1 volt RMS. I'm gonna hook, I am hooked up to the circuit, so I need to follow those guidelines. Procedure 7A. Find the current in the circuit by measuring the voltage across the resistor as before. Okay, do that. Voltage across the resistor. 0. 24258. The total current, how do we find that? Right, total current equals current through the resistor. Is voltage across the resistor divided by the measured resistance. I don't even remember what I had for my resistance value. Anybody remember what I had for my resistance value? Yep. 990.94 looks like. I'm gonna call that 0.245 milliamps. Voltage across the capacitors. And to do that, what it says to do is measure across both of them as if they were one single capacitor. Everybody understand that? 0.181 volts. Capacitive reactance. How do we find that? Right, Ohm's law, R equals E over I. Computed capacitance. Remember that formula? One over 2 pi f x sub c total. Zero 0.215 microfarads. Got it? Connect the capacitors in parallel and repeat step 7. Assume the parallel capacitors are one equivalent capacitor for the measurements. Enter the data in table 19-3 and the review questions. I'm not going to do the math for that. I'll let you guys do it since we've been through it, but I will show you how I would set up my board with the capacitors. Those in parallel? Yep. If I wanted to measure voltage across that equivalent capacitance of those being in parallel, all I have to do is pick any point that's in common on this side and any point that's in common on this side, right? So just as an example, if I was going to measure voltage across that, I can do it like this. I mean, I can even grab this resistor right here. That's going to give me capacitance across those 2 points because everything in this row is connected together, right? So anywhere on this row where I take a measurement, gonna be the same. Anywhere on this road, I take a measurement, it's gonna be the same. That makes sense? All right, well, I'll leave you to it to do the rest of the math for yourselves and finish out the review questions. You can turn those into me when you're done. On Thursday, take a quiz, right? Over the homework that we went over today. Yes, no, maybe. Chapter 18 quiz. And then after that, we'll look at the next lab, which is the one that I just handed out to you, lab 17A. And 4. If you finish up this lab today, whatever lab you have done, please hand them in to me before you leave so I can get your grades updated.
I'm gonna try to get you this other one out, so I don't see it wrong.
Sweet. Okay. Okay, I'll come back.